If you've ever seen a gorge or a slot canyon or some river in which bedrock is exposed, then you know that rivers do more than just move sediment and water. They also carve down into bedrock and carve the landscape and create the land forms that we are used to seeing around rivers, so building those deep valleys and those bedrock channels. As geomorphologists, we want to have a rule to understand how rivers evolve over time. And thus far, I've been talking about shear stress against the bed. And we'll get back to that because that's a very good way of thinking about the erosive or transportative power of a flow by being able to understand how much shear it's creating in that layer along the bed that can either erode material or move material. But today we're going to talk about a different framework, and that's called stream power. And so this is the power, so the amount of energy converted per unit time over a cross-section of a river channel. And to understand power, let's go back to a concept that's probably familiar to you from a physics class. Let's talk about energy. And so in energy, the common equation that we have is potential energy is equal to mass times gravitational acceleration times h, so mgh. And so this is an elevation. G, gravitational acceleration, is assumed constant so long as you are a constant distance or a pretty constant distance away from the center of Earth. And because even our big hills and mountains, we go up and down maybe up to, let's say, 8 kilometers to the highest peaks in the world. And that distance is still very small compared to the 6,371 kilometer radius of Earth. So therefore, we can assume gravitational acceleration is approximately constant. And then over here, we have m, which is just mass. And let's actually try to define mass and what we mean by mass with a fluid, because in a solid, we actually have a real object. And so let's take something that we're going to call a control volume. And so this control volume, you can think of as just an imaginary cube that sits inside a fluid column and that you can use in your mind to think, okay, this is the parcel of fluid that I actually care about. And this has this control volume, so there's a volume V, and we place line through it to indicate that it's this small enclosed unit volume. And it has dimensions. Let's just, for the sake of convenience, give it dimensions delta x, delta y, and delta z. And the material inside this control volume has density rho. So this is density. And density of water, in case you've forgotten, is 1,000 kilograms per meter cubed. Very easy to remember, comes straight out of the very nice definitions of the metric system. So water, 1,000 kilograms per meter cubed, you have some control volume of that. And so if we want to use that to rewrite this equation for potential energy, we can then say that P E is equal to mass, so now we have rho times volume times then same gravitational acceleration. And I'm going to use z because we've been using z for the elevation that we're considering, and so in many of the other parts of this class. So for example, for hill slopes, so this is just the elevation of the channel bed. And here we're just going to assume that the flow is quite thin. So actually I'm going to write this down, assuming that h, which is now going to be thickness of flow, which means that it's not the same h as this. This is just the h that we have for, I'm just going to say this is equal to z. So that's just the h that we have because I wanted to remind you of how it often occurs in physics classes. So it's not that same h, but so assuming h is thickness of flow, we have, if h is much less than z, then we can just ignore the fact that there's a little bit of difference between the riverbed and the water surface. And I like to think of the channel bed because that is the land surface that we care about in geomorphology. And the flow surface can fluctuate a lot depending on whether there's a flood or whether there's a low water level on a particular given day. So we have this potential energy, and what I want to know in a channel is how this potential energy might do some sort of work or might evolve the bed. And one thing we can think about is that if we have a riverbed, right, like this, and we have some point here, let's call this point x naught, z naught, and let's call this point out here x1, z1, then if a parcel of fluid is moving between these 2 points, it's actually dropping in elevation, right? So what that means is that if we have, at this level versus this level, we have PE naught is greater than PE of 1. And so therefore between point 0 and point 1, we have a loss of PE, of potential energy downstream. And then therefore this means that this is converted. And what is that converted into? Well, there are a couple options. Quite a lot of that potential energy might be dissipated as heat. So this heat can occur via shear between different layers. So shear, and we can think of turbulence. And all of that motion, the swirling motion inside fluids, is actually creating a decent amount of interaction between surfaces inside the fluid and friction. And so in fact, there is a term that's often called shear heating. And that is this energy being dissipated as heat. You can also convert it to kinetic energy. And so that kinetic energy could be related to the flow velocity, or it could be related to sediment transport, or it could be related to bedrock erosion. Now I'm going to call the flow velocity part here A, sediment transport B, and bedrock erosion C, just so I have a bit of room to describe each of these. So taking it back out here, A, I'm going to show why flow velocity is not a very likely option. And so KE, kinetic energy, is equal to 1/2 m u bar squared. So this is your velocity squared. So 1/2 mv squared is the common way you see it in physics textbooks. And at first blush, it looks like this is actually saying that, yeah, it would make a total sense for this potential energy to be converted into kinetic energy because the river has some velocity, so this could work really easily, right? Well, the issue here is that it's total energy that's conserved, not potential energy or kinetic energy. And so if we have our little section of channel right here, and so we have some sort of flow in and some sort of flow out, over a short reach of channel, the velocity and the mass, so I'm going to call it rho v, of fluid, are actually not really changing, right? There aren't new tributaries coming in, so the volume is staying the same. The channel slope is the same, and so the channel velocity ends up being the same. And so as a result, we have the same velocity going in and going out. And so since energy is neither created nor destroyed, If we generate new energy in this reach right here by, dropping the fluid from here to here, that potential energy becomes converted to other forms of energy, but it cannot be converted to kinetic energy to speed up the flow because the river is not accelerating. And you can think about this, if you prefer to think in terms of forces or stresses, that the driving forces of gravity carrying that fluid downhill are being balanced out by frictional forces from resistance against the bed and the banks, as well as internal resistance due to the turbulence in the flow. So, but primarily from bed and banks. So, what that means then is that flow velocity is not likely a major contributor. There could be some sediment transport, but likewise, if there is a constant slope and a constant velocity, then shear stress is the same everywhere. And because sediment transport is proportional typically to, basal shear stress, maybe to some power, then the sediment QS in and QS out are going to be the same as well. So we just have QS, QS. And so it's not very likely that sediment transport either. However, bedrock erosion is a real possibility because anything that comes in that might have been eroded from the bed before, that's just part of the sediment transport term. What did I do? I tried to undo this little blip down here, and I ended up breaking something. All right, there we go. So, as I was saying, so sediment transport is balanced, and then bedrock erosion, if there's some material that's already entrained, that's just part of that sediment transport term. And so bedrock erosion is a way of producing brand new material in motion. And so what that means is that before m equals 0 and u bar of bedrock, the newly eroded stuff, is also equal to 0 because it's not moving. And so then you actually are able to convert that potential energy into kinetic energy that then would cause the channel to evolve. And so in order to think about this then, what we want to do is know, well, what we want to know as geomorphologists is what is the rate of erosion? And in order to think through that, we want to answer the next question, which is, what is the, rate of potential energy to kinetic energy conversion? And so, in order to break this up a bit and make sure that I don't have just one crazy long video, I'm going to save that for the next presentation.